I'm currently working on an entirely new approach to HF Mobile, an electric dipole, and not finished yet, but gee, she's getting there. Now this, I had a few objectives in mind with this one. One of them is to do the high bands, like, you know, let's say 10 meters, just as well as the low bands, and also to have it in a way where you can just screw it on like you would with any other whip. Okay, so I'm 10 watts at 10 meters right now. Okay, come a little closer. Can you even see it's lighting up the lights? Okay, so yeah, great on 10 meters. Now I'm just going to stop that so I don't go blind. Okay, and it's not finished yet. All right, so yeah, what a crazy idea. So of course, well, where to begin? All right, so this is not finished. I'm just feeling it out. This will be able to be just screwed on like a normal antenna, whereas the, for example, the HF Tesla Mobile has to have active and ground connected. Okay, so instead of that, what I've done is, when it screws on, it's a 9-foot whip. I'm using the whip itself as my active connection, okay, but not as the antenna. And you might notice here there's some insulation and then copper sleeving. So it's going to be a bit hard to show this. This isn't a very thorough video, just a quick peep. Okay, so that copper sleeving goes here, and you notice the insulation stopped. This copper stopped. So that is one element of the electric dipole, but at the end of the element I'm going to add a lot of inductance so that it can tune in on the low bands as well. And in the center here is what I've been working on today. I've made 2 of them so far. This is a very complex dynamic capacitive system. So it does a lot like my regenerative coil design, except using capacitive plates instead, so that the inductance value stays very low, the magnetic inductance value. And that way I can get the benefit of the dielectric inductance feedback without having to have too much magnetic inductance. And so that's why this does the high bands so well. Now at the top of that, as you see, it connects again to another copper sleeve that goes up the antenna. Now, so neither of those copper sleeves are connected to the whip. Okay, the whip is my active source, but in order to make my special arrangement work for the feedback into the system, well, that was designed to have an active and a reference. Okay, so I gave it them. So it has the active source, like I mentioned, which is the actual whip, and it has its active output that goes to the top copper sleeve, and it's made its own reference by me giving it a bottom element that is not connected to the system, well, directly to the source. And of course, differences between what's going on the actual whip and the sleeve are all capacitively stored. So it is an electric dipole, and I'll explain that a little better. So for example, virtually, well, all mobile antennas are only half of an antenna, including the HF Tesla Mobile, right? We've got this fancy bit here and the whip going up, but it's half of an antenna because it's this that's changing its potential with reference to the vehicle body. So it depends where on the vehicle it's mounted and stuff like that, on how it all interacts and what your takeoff angle is, etc., etc. Whereas the electric dipole, pardon me, is a complete antenna. Okay, so the idea is that this is always opposite in its electric charge to this. So it's not about the direction of current flow, because of course, it's far too short for 80 meters, for example, for that to even factor in, isn't it? and that's why small antennas for the low HF bands are always considered inefficient. And also keep in mind that short antennas, a very small fraction of a wavelength long, offer an extremely high impedance to the flow of current. So when life gives you lemons, you make lemonade. So high impedance to current increases voltage. So this is what it's all about. And with my feedback loop system now as a dielectric inductor, or complex dynamic capacitor, however you want to call it, I can actually really take advantage of this. So it's an electric dipole. So if you can imagine, I'll go this way. You know how you can have a capacitive plate. So you've got a capacitive plate here and a capacitive plate here, and when there's a potential across them, the lines of tension are going across from plate to plate. Now, if you have this plate and this plate, if you actually open that one out that way and open the other one out that way, then you have an electric dipole. Okay, so like with this, if we freeze time and this was positively charged and this was negatively charged, the electric field lines from the positive would be coming around and terminating on the negative, right? Now, so essentially that's what it's doing, but of course it's doing it at frequency and constantly changing. Now we already know that changing electric fields, which or moving charges, which is what happens when this is changing and this is changing, it's equivalent to a moving charge. We know that moving charges create rotating magnetic fields around them. So when this changes its difference with this, it's the transition along the electric field lines that create the rotating magnetic field that we want for ham radio for a TEM wave propagation. And also we know we can determine the direction of the most effective radiation based on how those electric field lines are oriented, I don't know how to say it. So this will always have a low takeoff angle, even though it's on a car body. All right, so that's the idea. So its most significant radiation for a TM wave will be at 90 degrees to that system. Okay, now the thing is, of course, it's running very hot, even at 10 watts. So those electric field lines are not all just terminating on the other side. It's so hot, there's excessive fringing, so which is a bonus, because you can imagine these electric field lines looping out quite a long way, all creating a net rotating magnetic field for a TEM wave. So, of course, it's still a compromise, it's a mobile, but by golly, it's a good one. 7.3. Just realized I should demonstrate 80 meters as well, so wait for it to start. There you go. 80. So she's doing good. So this will do the best of both worlds. And what a unique approach. That's 80 meters, right? What a unique approach to HF mobile. So yeah, she's not finished, but I won't necessarily have that big massive white bifilar conical coil, but I will be increasing the inductance at the So basically the idea is the end of one of its electric dipole elements will have inductance that's kind of capacitively coupled to chassis ground, but that it can tune into, but it'll be so high that it can never get through. Like the amount of inductance on this thing is insane, but without it, I couldn't tune up on 80 meters. I could tune on 40 with the inductor as it was, but that has hardly any magnetic inductance because of the nature of the design. But this solves the problem. But of course, for 10 meters, for example, then it just doesn't see this. Brilliant.